Inside silicon, the technology behind everything.
All right, welcome. Today we're diving deep into one of the most talked about technologies on the planet, artificial intelligence. I mean, it's everywhere, right? In our phones, our cars, and it just feels smart. But how does it actually work? We're going to pull back the curtain and look at the gears, the fuel, and the physical engine that makes it all possible. You know, when you ask a chatbot a question and get this perfectly coherent answer, or you type a few words and get a stunning piece of art, it's easy to feel like you're talking to something that's, well, thinking. It seems like there's a real mind in the machine. But here's the billion-dollar question we have to ask. Is it really thinking? Well, the short answer, it's a hard no. What feels like intelligence is really the result of three core things working together at a scale that's almost impossible to imagine. Incredibly fast math, gigantic amounts of memory, and super specialized silicon chips. That's it. That's the core idea of this entire explainer. Okay, so first things first. Our goal here is to strip away all the magic and the hype. To really get a grip on AI, we have to stop thinking of it as some kind of artificial brain and start seeing it for what it truly is, a masterful piece of engineering. And this is where things get really interesting, right? This chart just lays it all out. When we, as humans, reason, we're dealing with deep stuff like meaning and intention and truth. And AI, it's playing a completely different game. It doesn't get meaning, it just recognizes statistical patterns. It has no intention, it just calculates probabilities. And it has zero concept of truth, only a relentless drive to optimize its answers based on the patterns in its data. All right, let's talk about the first piece of the puzzle, data. If you think of an AI system as this high-performance vehicle, then data is its fuel. Without it, the most powerful AI model in the world is just an empty shell, going nowhere. And this is such a critical point to understand. An AI doesn't read the entire internet and learn that Paris is the capital of France. Nope. What it does is analyze all that text and figure out that, statistically, when the words capital of France appear, the word Paris is extremely likely to follow. It's all about connections and relationships, not actual knowledge. So what kind of relationships are we talking about? Well, for a language model, it's all about which words usually hang out together. For an image generator, it's about which blobs of pixels tend to mean cat versus dog. For a stock market predictor, it's about which signals correlate with a price going up or down. And that's why a model's behavior, its weird quirks, its amazing talents, and its frustrating blind spots, it all comes back to the data it was fed. Now, check out this quote from people who actually build this stuff. It really puts things into perspective. We hear all the buzz about fancy new AI models, but the reality for engineers is that most of their time and money is spent just cleaning, labeling, and prepping huge data sets. Because at the end of the day, the engine is only as good as the fuel you put in it. Okay, so we've got the fuel, which is data. Now, what about the engine? Well, that's the math. This is where all the heavy lifting happens, inside what we call neural networks. But again, let's just push that brain metaphor aside for a second and look at the raw mechanics. This is going to sound way too simple to be true, but this is basically it. This is the core operation behind every advanced AI you've ever used. For every little piece of the network, it takes some numbers, multiplies them, adds them up, and then puts them through a little function that basically asks, is this signal strong enough to pass along? That's literally it. The magic isn't in some complex, mysterious calculation. It's in doing this super simple sequence over and over again, millions or even billions of times. So how does the network learn anything? It's all about these things called weights. You can think of them as billions of tiny little knobs on a giant control panel. During training, the AI makes a guess, sees how wrong it is, and then uses some clever calculus to figure out exactly how to turn each one of those billions of knobs, just a tiny, tiny bit, so it'll be a little less wrong next time. It's just pure, relentless numerical optimization. Yeah, the name neural network is, let's be honest, a little confusing. The original idea was kind of inspired by how we thought the brain worked, sure, but modern AI, it's all applied math and computer engineering. We are not simulating neurons here. We're building incredibly efficient, massively parallel math machines. So we have our fuel, data, and we have our engine, math. But what does this engine actually run on? That brings us to our final and maybe most important piece, silicon. This is where the abstract world of algorithms slams right into the hard reality of physics. First, it's super important to get that AI has two totally different life stages. You've got training, which is this insane brute force process of turning all those billions of knobs. That can take weeks, even months, on a supercomputer the size of a building. Then you have inference. That's actually using the trained model, and it has to happen in a split second on your phone or a server. And these two jobs need completely different kinds of hardware. Think about the main chip in your laptop, the CPU. It's like a Swiss Army knife. It's pretty good at a lot of different things. But the simple multiply and add math that AI does over and over again, the CPU isn't great at that. This very specific need for massive parallelism is why the industry pivoted to using things like GPUs, which were first made for video games, and now totally custom-built chips like TPUs that are designed to do one thing and one thing only: AI math incredibly fast. Now, this next part is maybe one of the biggest insights in modern AI hardware. We've actually gotten so good at the math part, the multiplying and adding, that the main bottleneck, the real traffic jam, isn't the calculation itself anymore. It's just getting the data from the memory chip to the processing chip fast enough. It literally takes more time and energy to move the data around than it does to do the math. And so, this whole memory problem is what's driving all the coolest innovation in chip design right now. It's why you hear about things like high bandwidth memory, where they stack memory chips on top of each other to create a super fast connection. It's why companies are using chiplets and advanced packaging, all just to bring the memory and the processor physically closer together. The future of AI performance is all about solving this data traffic problem. You know, for the longest time, the mantra in AI was just bigger is better. More data, bigger models. But we are hitting some serious walls. And if you look at what's really holding us back now, it's not the algorithms, it's the raw physics of it all. It's having enough power to run these giant data centers and enough cooling to keep them from melting down.
So what does this all boil down to? It means the way forward is changing. The next big breakthroughs probably won't come from just making models bigger. They're going to come from smarter algorithms, more efficient hardware, and a really clever co-design of software and silicon working together. The future is going to be defined by real-world engineering trade-offs, not by the latest hype cycle.
So if you take away one single thing from all of this, let it be this. For all the talk about superintelligence and fancy algorithms, the next decade of AI progress might be defined more by physics and materials science than by computer science. The future of artificial intelligence is fundamentally constrained by physics. And understanding that, well, that's the key to understanding where all of this is truly headed.
Inside Silicon, the technology behind everything.